Hello everyone, I'm Pranali Surkar. I'm working as an assistant professor in the Department of Electronics and Communication Engineering at Marri Laxman Reddy Institute of Technology and Management, Dundigal, Hyderabad. So I welcome you all in today's video lecture, which is based on the course Analog CMOS IC Design. And today we will discuss about the derivation of MOS IV characteristics. Before that, we have seen the threshold voltage, which is the base of this derivation. We should know what is meant by threshold voltage, so that we have discussed earlier. So in today's topics, we are discussing about the MOS IV characteristics, and we will begin the derivation. So what we are basically doing in the derivation of this particular MOS IV characteristics is how to begin. So for that, we will consider a semiconductor bar. So this is a semiconductor bar in which we have shown the current, which is this bar is carrying this current I over here, and it is having the mobile charge density along with this direction of the current is denoted by, we are denoting this as a QD. So QD is nothing but the mobile charge density. The unit is it's coulomb per meter. And also this V is nothing but the velocity of the charge meter per second. So this is denoted by small v over here. So if you want to find out the current, so passing through this particular semiconductor bar, so this is the formula for current. So current is nothing but the charge density into velocity. So here we have shown that this current is passing through, the charge carriers are moving with the velocity of v meter per second in 1 second, and then they will travel the v meters. So in 1 second, we'll see that all the charge containing this v meters of the bar, they are passing through the cross section area. So from this to this, it is traveling in 1 second. Here we have the two figures over here. So this is nothing but the n-channel MOSFET. You can see that these are the this is the source and this is the drain, which are heavily doped regions, and here this is the p-type substrate. So this is basically NMOS, and here we have kept, in the first diagram, we have kept source and the drain voltages equal. So here we have seen that we can see here the source is connected to ground and drain is also connected to ground. So here in the shorter way, with the symbol we have represented it. So this arrow indicates that it is a source region we have taken over here, and this one is the drain. So both the source and drains are connected to the ground in this first case. Then in the second case, we have connected the voltage at the drain terminal. So here we have unequal source and drain voltages. So source, as usual, like the first case, we have connected to the ground, but for the drain terminal, we have applied some voltage VD. Now we will see that what will happen when the drain is at a 0th potential, means when we are considering the drain potential is 0 or the grounded, and what will happen when we are applying some voltage to the drain terminal. So that we will see over here. So let's assume that inversion will start exactly at VGS is equals to VTH. Now here VGS is nothing but the gate to source voltage, which will be considered as an input voltage, and VTH is nothing but the threshold voltage. So threshold voltage means it is the voltage at which threshold voltage. So this is the voltage at which there is a formation of the inversion layer, and we can call it as a channel. So at this particular point, we'll consider that VGS is equals to VTH. Now the inversion charge is at VGS is greater than or equal to VTH. So whenever there is an input voltage, VGS is greater than or equal to VTH, we can say that there is a inversion charge flows. Now here, for this particular case, when VGS is greater than VTH, the additional gate voltage credits the mobile charge in the channel. So there is a creation of mobile charge when VGS is greater than VTH, means threshold voltage. Now here this gate oxide will act as a capacitor. So capacitor, we all know that there are two plates, and in between the dielectric will be there. So in this case, this gate oxide will treat as a capacitor. Now whenever there is a drain voltage is equals to 0, or we are keeping that drain voltage to the ground, so there is a uniformity in the charge channel. Means whenever there is a drain voltage 0 or ground, the channel potential is same everywhere to the channel. Means this is the channel. Suppose for example, here the channel length is from 0 to L. So throughout the 0 to L, there is a uniformity, and the channel potential is same everywhere in this channel. So inversion charge density, if you want to find out, so let's take a capacitive relation in this case. So here we will get that QD means this is the charge density. So this charge density is equals to WCox VGS minus. So this VGS minus VTH is nothing but called as overdrive voltage. This is called as overdrive voltage. And Cox is nothing but the capacitance of the gate. And this W is nothing but the width of the channel. So Cox, we can say that it is a capacitance of the oxide layer per unit area. So this is called as effective gate overdrive voltage, the complete VGS minus VTH term. So here this is the charge density formula whenever there is a uniform channel. Now we'll see that what is the effect of drain voltage when it is greater than 0, or whenever it is we have applied some voltage at the drain terminal. Now we'll see that what is the effect of the voltage. Now whenever there is a voltage drain voltage applied, so there is a two conditions. Means channel potential is 0. So here whenever we are applying some gate voltage, so in this case for this is source and this is the drain. So towards the source, the channel density will be 0, channel potential will be 0, and towards the drain, channel potential will be channel potential will be VD. So here this channel potential varies with position X. Means here we can say that this Vx is varies from 0 to L, because we are considering that length of the channel is L and it is varying from 0 to L. So at this position, for example, if you are taking any position X over there, so there is a gate channel voltage. So in this case, the channel will be at the fixed potential. Gate will be at the fixed potential. So VGS of X, if you want to find out, it will be VGS minus V of X. Now there is a local inversion channel charge density also present. So this will become QD of that particular position, means X position. So here just we have to add, instead of VGS minus VTH, we have to add that particular voltage. For example, here in this case, suppose if we are considering this particular position at X, so then we instead of VGS minus VTH, we have to consider this voltage also, means V of X also we have to consider. So the whole equation becomes QD of X is equals to, means density at that particular point X is equals to WCox VGS minus V of X also minus VTH. Now if you have already studied in the semiconductor physics, we know that current is nothing but the QD into V. Here also we have seen that the current is nothing but the charge density into velocity. So here we will just consider this QD at particular point X and velocity at that particular point. So here we have written negative sign. So negative sign is just indicates that we are considering the electrons as a charge carriers. Then so ID will become, this is the formula we are putting over here. So minus Cox VGS minus Vx upon minus VTH, and this Vx is nothing but V. So now again there is a velocity field relationship, means velocity is directly proportional to the electric field. So here so V is directly proportional to V, so we can write is V is mu E, so where mu is nothing but the mobility. Its mobility. So if you want, you can suppose you are considering the electrons as charge carriers, you can write the mu n. Otherwise, if holes are the charge carriers, then you can write the mu p. So here we have considered the NMOS. So we will consider the mobility of the electrons over here. So this electric field along the channel if you want to calculate. So this is nothing but the rate of change of potential. So we have written Vx is equals to minus dVx by dx. Now this complete equation of the E we will put over this equation, and also in the ID equation. So ID will be equals to, we know that already we have written over here. So V is our mu n E, so we will put over here. So you will get mu n dV by dx. So this complete value we will put in this equation. So we'll get ID is equals to W Cox again. VGS. So this minus sign and this minus sign will become plus over here. So we have not written any negative sign with the in front of W. So in this case here, now we have to apply the boundary conditions. Now what if we consider the boundary conditions, then at the source end it will start with the 0, and towards the drain, so we have considered this, its output voltage VDS. Now this limits we have to put over here. So here we will multiply both sides by dx, for example. So in this case, this dx will be multiplying with both sides after the next step. ID will be multiplied with the dx, and this will be dx gets cancelled with the dx. So here also, here also. So multiplying both sides, we will get this steps. Next step, ID dx, and here also dx division denominator dx will get cancelled. So here you will get 0 to L. Now we are integrating this, and as well as we are putting the limit also. So if you see that this L, so L is equals to this L left hand side. So this is 0 to L ID dx. So we can put over here, ID is nothing but constant, so you will get 0 to L dx. So you will get ID into L over here by after putting the limits. So left hand side you will get the ID into L. So for example, if I'm writing over here, so ID into L you will get, and after integration, and for example now if we want to calculate this VDS, so this is nothing but the constant term, so we'll keep outside. So this is nothing but the W Cox mu n. Now we have to integrate this. So 0 VDS, 0 to VDS, VGS minus VTH. I'm just separating the terms here. dV also minus again 0 to VDS V dV. So here you can get this again constant. So here you will get VGS minus VTH into VDS after putting the limit, and here you will get V square by 2. So this will term also becomes VDS minus VDS by 2. So after putting this you'll get mu n Cox. So this L will become L, we can shift to the right hand side. So after that the rearranging the equation, you will get ID is equals to mu n Cox W by L, VGS minus VTH VDS minus V by 2 VDS square. So this is basically the linear equation, current equation in the linear region, or we can say that it is a current equation in the ohmic region or triode region. Now here in this case, we are basically doing the derivation, means we have to find out the current equation in the linear and saturation region. So I have not explained that the current equation in cutoff region, because we have already seen that in the cutoff region transistor will be in the off condition, off state, so there is no current flowing through it. So ID value is nothing but the 0. So we have, our goal is nothing but to find out the current equation in the linear as well as saturation region. So up to this we have seen the current equation in the linear region. Now we will move towards the saturation region. So if you see again these two diagrams, there is a pinch off behavior shown in these two diagrams. So when pinch off behavior happen, whenever we are applying again when we are increasing the VDS more. So here from earlier results we have this channel charge density. So if at the drain end pinch off occurs, so when there is a condition, for example, if V of X over here, if it is equals to VDS or equals to VGS minus VT, so in that particular case your QD potential is tends to 0. Now in this case, towards the drain side, here you can see towards the drain side, here the depletion region forms. Here we have written depletion region forms, and the channel is getting reduced towards the source side. So we can see that there the channel is no longer inverted. It is basically pinch off towards the source side, sorry, towards the drain side, and the channel is getting reduced. So now previously, suppose your length of the channel is 0 to L. Now at this particular point, your channel is till 0 to X2. So previously it was up to X1, and now it is X2. So here again we'll recall this current relationship. We know that ID is nothing but the how much density is there, and what is the velocity of that particular charge. So if you want to find out, this V is equals to nothing but ID upon QD. Now if you want to maintain the same current ID, this V should be increases. Now what will happen near the pinch off point? So in pinch off point, here this is nothing but the pinch off point, we can say X2. So in this point, your electric field becomes very large, and the electrons are getting accelerated very strongly. So there is a condition when pinch off occurs is, so there is a condition like VDS, means drain to source voltage, should be greater than or equal to VGS minus VTH. So at this particular point, we can say that this charge density becomes 0. Now this charge effectively ends at X is equals to L dash, means why L dash we have taken? Suppose your previous charge channel length is 0 to L. Now we will consider that instead of L, your charge now the channel length is up to L dash. So now our limits will be 0 to L dash, not up to L. So here in the linear region we have seen this, but in the right hand side we have to consider voltage 0 to VDS, that we have already. Now in the left hand side, your length is not L, it will be L dash. So 0 to L, again here you will get this left hand equation is ID into L dash. So here for example, again we have to consider ID is here constant along the channel. So it will be ID L dash, but this L dash and L are having approximately same value. So we have consider at the last we'll consider that L dash is nothing but the L. So if we see the right hand side, again this whole term is the constant term, will keep outside, and now your voltage is nothing but VGS minus VTH, means instead of VDS we have to take the limit up to VGS minus VTH. Now again, if you want to calculate this, again after splitting the integral, this is the first part and this one is the second. Now instead of just VDS, we have to replace VDS by VGS minus VTH. So in the second term, this if you see here, so it will be VGS minus VTH whole square, and here also VGS minus at this particular point, and here VGS minus VTH by 2. So if you minus this term, you will get that this minus of this term. So you'll get VGS minus VTH upon 2. So you can get the value, sorry, it's square term only. So finally you will get that ID is nothing but the, again L will go to the right hand side, this L will go to the right hand side, and this V minus Cox W by L dash VGS minus VT H whole square, because this V complete one VGS is we have subtracted this 1 by 2. For example, half VGS minus VTH square is subtracted from this 1 VGS minus VTH whole square. So we are getting the term again half VGS minus VTH whole square. So this is the formula for saturation region current equation. Now as we have seen that L dash is nearly equals to L if we are considering the long channel devices. So this difference is very minimum. So again we will consider as we will replace that L dash by the L. So here final equation we are getting at the saturation region. So this was all about the linear current equation and the saturation current equation. So this is the very important derivation exam point of view. So where we have to find out the current equations in all the three regions, but we are not going towards the cutoff region. We can just simply say that there is MOSFET is off in the cutoff region, so the current value will be 0. We have to just focus on the linear region as well as saturation region. So this was about the both the regions current equation. So in the next lecture, we will see the different stages: common source, common drain, and common gate. Till then, thank you.